Okay, now that we've buzzed the sample WinAFL harness included, it's time to put together some of those skills and target a actual real target. In this case, we're targeting a Windows component, and it's going to be a certain functionality that's a part of Windows Event Viewer. When we look at this target, we're going to leverage some of the stuff we did with WinAFL before, but there'll be a whole heap of new things we'll have to account for to fuzz this target. And the first steps is interacting with the target and then getting it to be fuzzable. And then once we're fuzzing it, we can look into improvements we can make to enhance performance and things of that nature. And then we'll look into fuzzing it with a snapshot fuzzer, and we'll talk about snapshot fuzzing with the different ones available, including hypervisor and emulation-based approaches, and the sometimes extra care we have to put into our harnesses when using those methods. So to begin with, if I open up Event Viewer, um, we're going to target the functionality that occurs when it passes a EVTX file, which is an Event Viewer file. First, I'm going to generate a sample one. I'm going to highlight just two entries. You can highlight multiple more if you like. Right click, save selected events. I'm going to save that in my user's documents as my evtx.evtx. Actually, it's saving in my desktop. Once I hit save and OK, I see in my desktop this evtx file. And now if I double click this evtx file, it'll automatically be loaded and passed by Event Viewer. You can see it's here now as a saved log, and the events that were in it have been passed. Now if there's any bugs that come from parsing this file that we find during fuzzing, this could be both a privilege escalation and a RCE vector. Because for starters, Windows Event Viewer actually doesn't run as your logged in user. This may differ based on what operating system you're using, but typically it'll run as local service, which can commonly be easily privilege escalated to system. Not always though, but still it doesn't run as your current logged in user, so you can get something out of that. Additionally, it would be a RCE for multiple reasons. The first reason is that it's not expected behavior that opening a EVTX file will get code execution on your machine. So if I were to email someone this file and they double clicked it and I got code execution, that's not expected behavior, so that would count as an RCE. But also, it's quite common in organizations to have multiple workstations forward their event logs files to a central set of servers somewhere that will collect collect the EVTX and event file data from those other machines and pass it locally. Um, so potentially, if I could send such a event log file, a malformed one, to a central server somewhere that's going to pass it, trigger a bug, and get code execution, then that is quite clearly an RCE in that scenario as well. But I do want to make clear before we jump into this that the goal of this is not for you to walk away with just an EVTX fuzzer, right? Everyone will have their own targets after this training. Some people will target kernels, some people will target network related passes, file passes, hypervisors, maybe even iPhones or Android devices or IoT devices. And a lot of the techniques and challenges that we'll have to overcome in fuzzing this target will be globally applicable. They're general steps that you would typically do when harnessing or fuzzing any sort of target, really, no matter what it is. It's going to involve reverse engineering. It's going to involve sometimes carving out functions and calling them directly and handling global state and unless you go the route of full system snapshot fuzzing, which we have an example on using NixFuzz as well. So we try to cover as many scenarios as possible and the techniques and that you can use to help you with your own fuzzing adventures. And we're also going to look at some unique approaches, unique in the sense that I don't see many people doing them, um, to obtaining perf and making things snapshot fuzzable. So that'll be fun as well. So the first step, the first thing we need to know is, okay, I know if I double click this file, it triggers passing off it, but like we don't want to fuzz by just double clicking files, right? I'm not going to sit here and generate a bunch of EVTX files and just go through double clicking them and waiting for one of them to crash. You know, in our GDI plus WinAFL example, we're hitting over 100 executions a second. By double clicking things, I'm probably getting like one execution a minute. By the time I double click it, wait for it to load, and then generate a new one, right? And we don't have coverage or any of that. So how can we actually fuzz the passing code? Well, first of all, I need to know where that code lives. I need to know if it lives in an exe somewhere. I need to know if it lives in a DLL somewhere. Like, we need to identify where the actual code that does the passing lives on the system. And there's multiple ways you can do that. Whether you just attach a debugger to the process and step through it, seeing where it accesses this file on disk, or things like that. But in our case, I'm going to get started with Procmon, because Procmon can be used to trace file system and network and registry related events quite easily. So I'm going to launch Procmon, and the filter I'm going to use is I'm going to say notify me of anything that happens where the file path contains my evtx.evtx, because that's the name of the evtx file that I'm loading from disk, and I want to catch anything that tries to open and read from this file. That should tell me which code is responsible for at least opening and reading this file into a buffer, which should be very close to the passing code. I include that here. Okay. Now I need to trigger the behavior. So I'm going to double click the evtx file. Wait for it to finish passing. Done. Now let's look at Procmon. Sorry, my Procmon didn't capture anything because path should have contained that. Let me double check. Okay. Let me just restart that capture. And let me reset the filter entirely. Make sure things are being captured. Okay. Let me reapply that. Make sure the path contains... sorry. I had a typo. I did my EVTS. It should be my EVTX. Okay, that should fix things. I'm going to have to close this first and then rename it. Okay, my EVTX.EVTX. Yes, the file names clearly should match. Let's add that in. Let's get rid of Explorer because I don't care about that. And let's double click it again. Okay. Cool. Now I can see a bunch of entries, bunch more entries. And we need to clear some of the clutter. So first of all, Smart Screen is Windows Defender. Windows Defender. We don't care about Defender. We can exclude that. Now we see SVC host, we see some create files, and actually these ones are interesting, the read files. Let me see if I can just increase the font. Might have to just minimize that and relaunch it. Okay, the read file entries, I'm going to right click and hit highlight, because they're the interesting ones. They're the ones that are actually reading our file into a buffer. Now I can see here it's reading 8 bytes, and then down here it's reading 128, and then it reads 128 at an offset. and then still 128, then 8 again, 8 again. Well, there's a big read over here of 65,000 bytes. That's interesting as well. So we've identified some reads that are occurring on our file. Now, if I go to the first one and I double click it, if I look at the stack is going to show me where the code is. It's going to start from the end here, which is the file filter drivers that are actually going to access the file on disk. And as I go down the stack, I see the NT kernel, where it handled the NT read file system call. And then I see NT read file in NTDLL being called. And I can see that was called by kernel base, where the read file API was used. And just underneath this is the location that called read file. It's in revtservice.dll. This DLL lives in C drive Windows System 32. And it's at the location of determine file type plus 0x278. Now this is the offset into the DLL where the read file occurred, or the instruction after the read file. Determine file type is a label, and 0x278 is an offset to that label. Now you can see here, I actually have symbol information. It says get log object, registered log handle. These are all symbols. Lots of Microsoft code comes with symbols. So when you have symbols or you're analyzing Windows code, you want to make sure that you're leveraging that information. Of course, we could still work with this without symbols. It'll just take a little bit more reverse engineering effort. So let's take a look to analyze how we can set up symbols. If you go to, which one is it? Tools, no, options. Okay, under options, there's configure symbols. In configure symbols, may be hard to see, so I'm just gonna spawn up a notepad where I can zoom in. The first value is a path to dbg help. I put dbg help at this path. Now this dbg help file is from the Windows debugging tools, which is from the Windows SDK. So if you download the Windows SDK, when you go to install it, there's one option you can tick to install the Windows debugging tools. And I think by default that installs it to somewhere like C drive, program files, I think x86, and there's like Windows kits, and then it'll be either 10 or 11 based on which version you have. And then it'll be like debugger, x64, and then there'll be dbg help.dll there. So you need to point it to the path of the dbg help from the Windows SDK. And then the second one is your symbol path. Now, this is my symbol path. Where you do serve, asterisk, and then a folder on your disk where it can cache symbols. So I created the folder C drive symbols. You just need to create this folder such that it exists, and then you can put it here. And then asterisk, and then the URL to the Windows symbol server, which is msdl.microsoft.com/download/symbols. And this will be your symbol path. And then when you download symbols, they'll be cached in your C drive symbols folder. So if I browse to my C drive symbols folder, you'll see it's got, cmd.pdb, advapi32, Intel's kernel. It's got all sorts of symbols that it has previously loaded and cached on my disk. And then you can hit OK. And then the next time you open up the stack trace view, at the bottom left here, you might see that it's downloading the symbols. And you'll wait for it to finish downloading, and then you'll see this symbol information. So, based on the symbol name, even just by guessing, I can see here the label is determined file type. And we know that the read is reading 8 bytes. So I can just take an educated guess here and say that there's supposed to be some sort of header information in the first 8 bytes of the input that determine what file type it is. Now, if we're thinking why does it need to know the file type, It's because there's multiple formats of event files. There's EVTX, I think there's just standard EVT, and there's something else as well. But we can see this. I can open up Ghidra. I'm going to open up Ghidra on my main machine. Now in Ghidra, I've loaded the DLL already. And in Ghidra, you can also load up symbols. And once you've set your symbol path by going to Edit Symbol Server Config, and under Symbol Server Config, you hit the plus and you add the that msdl.microsoft.com symbol server URL. And you can also provide it the location of a folder for local symbol storage where it's going to be cached. You can hit OK, and then you can go to Analysis, One Shot, and do PDB Universal. But to hit that, you're going to have to be on some code. So I'm just going to jump to the .text section, which takes me to some code here. And I can do Analysis, One Shot. Actually, I might have to have the listing view. In the listing view, clicking anywhere on a function code, I can do Analysis, One Shot, PDB Universal. Now, I've already done that, so I've already got symbols. And I'm going to focus on the decompiler view. So we know that the first label that did the read was in determined file type. And we know the offset was, well, what was it? It was 0x278. Now in Ghidra, I should be able to just hit G and do the label name, which is determine file type, do plus, and do 0x278, I think it was, and hit OK. And that takes me to here. If I look at the listing view, I'm going to do it on the listing view actually, and that takes me to this address. I'm going to highlight it and jump back to the decompile view. And I can see that there is a read file here in the decompile view. And if I highlight it, Ghidra actually tells me what the parameters to read file is. And the third parameter is the size. And I can see the size here is hard-coded as 8. So this must be the read file of the first 8 bytes of our target. Now, if I didn't know what read file was, I can trace it by double-clicking it in the listing view and see that it's getting read file from this API MS RINCore file DLL. And this is actually going to just end up redirecting to kernel base. And you can follow that if you attach a debugger to the target. And if I run on Google and just did read file MSDN and hit the first function, the first result, it tells me that read file takes a handle, then the buffer, then the number of bytes to read, etc. And it tells me what the parameters are. MSDN has API documentation for a lot, and that's pretty invaluable when reverse engineering Windows code. Unfortunately, if the functions you're looking at aren't Windows APIs, it's up to you to reverse engineer to figure out what the parameters are yourself. And we're going to be doing that as well. So if we go back to where that 8-byte read was happening, we know that this second parameter here, which is local_30, is going to be the buffer. So I'm going to rename that to user buffer for user controllable buffer. And I can see that there's actually some checks being done on it. There's some checks here checking if it matches this long hex value. And there's different paths the code can go down depending on if it matches that value or not. And the reason for this is if I go back to the function that calls this. Now, how can I do that? Well, if I go back to here, I can see that the function that calls determine file type is getLogObject plus 0x20. So that's what called determine file type. But additionally, if I just highlight determine file type and I look at the function call tree in Ghidra, it also tells me that there's two incoming, there's one incoming reference, and it's in getLogObject. So I can just double click that, and that takes me to getLog object and the location where determine file type was called. And you can see how symbols helps out a lot here. We can see that it calls determine file type on something, and then based on the result, it'll either open external EVT file, open external EVTX file, or open external ETL file. So at this point, we know that the first 8 bytes of our input are going to determine which function opens the file, the ETL, the EVTX, or the EVT. So that's something our fuzzer can influence. We can hardcode those 3 different results as magic byte values in our fuzzer that it can switch between in the header. So say we wanted to fuzz getLog object. Well, here's the thing when determining which function to fuzz. Ideally, it's going to be a trade-off between how deep you fuzz and how hard it is to harness. So this 8-byte read would be extremely easy to fuzz, right? It takes one parameter, which it thinks is a string. Let's see what happens to that parameter. It checks if the file exists. It gets opened with create file W. And then if I highlight the handle to that, it gets read, and then it gets used in a comparison. So fuzzing this first 8-byte read is extremely easy. I could probably just call determine file type directly with the path to the file on disk, and it'll just, load it up and read it. Now, it's not actually that easy. We'll look into why and how we can overcome those issues. But disregarding those issues for now, that would be very easy to harness still. But the problem with that is we'd only be fuzzing the first 8 bytes because that's all that this function reads from our buffer. It just reads the first 8 bytes. So by just fuzzing this function, we'd be missing out on all the other reads that happen down the line in other functions. Perhaps in this open external EVTX file function. Perhaps this does more reads. How can I fuzz both the first 8 bytes in determined file type and any other reads that happen in open external EVTX file? Well, this is where you have multiple approaches to think of. The first one could be, well, if I want to fuzz both of those functions to fuzz more than just the first 8-byte read, what if I just fuzz getLog object? What if I write a harness that can call getLog object and call all the functionality that getLog object calls, including determine file type and open external EVTX file, properly? That means we'd be able to hit this function and hit all of the functionality that it contains and fuzz it. Now, that's one idea. Another idea is saying, okay, I'll fuzz determine file type, and then in my harness, after I call determine file type, I'll get the return value and I will call open external EVTX file directly. So that way we're not calling getLog object. Instead, we're figuring out the parameters to determine file type, calling it directly, and then refining the parameters to open external EVTX file and calling that directly, and then fuzzing those two functions separately. That could work as well. Additionally, we might say, okay, but let's look at some of the larger reads. Let's look at this 128-byte read. Where does this happen? If I view the stack, this happens in file view readin, which happens in file, which happens in open external log, which happens in getLog object. Okay, so if I call getLog object and I use that as a function for my fuzzing, I will hit the 8-byte read and I'll hit this 128-byte read. So I'll be fuzzing, 128 plus 8 bytes. That's more, okay? So we have a higher chance of hitting more functionality and more parsing functionality. What about that big read that we saw further down? This read here of 65,000 bytes. That's pretty good. There might be lots of parsing happening on these bytes. So that would be something we want to make sure we fuzz as well. When looking into this actually doesn't have getLog object as one of the stack functions. Instead, it goes to file read record, and then native log query result, and then merged log query result, and then query next, and then EVT RPC query next. Now, There's a couple things to note here. One is that since this large read happens in a completely different function, presumably if we went before to fuzz get log object, we'd also have to pick a function here, maybe query next, maybe read record, if we can just call read record directly on our EVTX file or something similar, to make sure that we hit this large read functionality and parsing as part of our fuzz session. Additionally, we could also hit something further up. Now this EVT RPC query next is an RPC function. And actually, if I looked at the first 8-byte read, if I go far enough down the stack, we get to EVT RPC open log handle, which is another RPC function. Now you might be thinking, why can't I just fuzz them over RPC instead? Now, presumably you could do that, but there's problems with that. First of all, RPC happens over networking, and calling a function over networking and then having to deal with trying to get something like WinAFL to attach to the target process to trace coverage and things like that is a pain, and it's slower. It'd be much easier to just call this function directly, which, again, we can do. It's up to us to determine which function we want to harness. Sometimes calling a higher level function like EVT RPC open log handle and saying, I'm going to harness this function, can be a problem because you might try to harness it and then realize that it does a lot of things that you have to account for in your harness. So there's a lot of extra checks and stuff that you have to manage. Because if we call this function directly, it's going to be expecting to run in the context of RPC. It's going to be expected to run perhaps in the context of a process that runs as local service in this service process. And there may be a whole bunch of other code not relating to parsing that's going to slow down your performance. If the parsing all happened in getLog object, you would gain zero benefit to pass to your finding crashes by harnessing further down the stack. You would just be hitting more and more code that's irrelevant to the parsing or to your fuzz session. So that takes a little bit of reverse engineering and just trying things to determine how far down you want to go. You can always start by trying to go down further down the stack, and if you have issues, try to tighten up closer to the parsing functions you're trying to target. For this exercise, we're going to look at fuzzing getLogObject and another function directly, but then we're going to circle back and look at how we could fuzz perhaps this RPC open log handle function directly, so that we can compare the approaches. So the first step, say we're going to start with fuzzing getLogObject. I know that if I can call getLogObject in my own code, I will hit this 8-byte read, and I will also hit this 128-byte read, because they both share the same getLogObject stack entry. So we're going to start by harnessing that. So the first thing we need to do is write our own code that can call getLogObject, which means we need to reverse engineer getLogObject to find out the parameters, because how can we can't call the function without knowing the parameters. So what we're going to do in order to do this is there's a few things we need. We're going to create a function pointer to getLogObject. How are we going to do that? Well, say we have revt service.dll. Now, mind you that the offsets that I'm working on are from the specific version of the DLL that I have provided. But you can feel free to follow along the steps using your own revt service on your own operating system. The offsets may be different and there may be certain quirks to it, but for the most part, if you follow through the steps, you should be able to get it working as well. Revt service will have the function, right? getLogObject. And we'll have it at a certain offset, say offset 1234. And that's an offset from the base address of revt service. And that offset's going to be static per version of this DLL. Now, if I know that getLogObject is at this offset of revT service, then my harness, right, my harness.exe can load revT service into my own process space. And with revT service loaded into my own process space, I can create a function pointer. I can be like function pointer equals to revT service plus 0x1234 and cast that as a pointer to getLogObject. Yeah. I'll show what the implementation of this looks like, but essentially your harness can load the DLL directly into our own process space. And first of all, if getLogObject was a exported function, I could just use the getProcAddress API from Windows to be like getProcAddress, getLogObject. And I think the first one will be like a handle to revT service and do like that. And this will return the pointer to getLogObject for me. But if it's not exported, which hint hint, it's not exported, it's a private function, we can't use getProcAddress. At least I don't believe we can. So in that case, we need to create our function pointer ourselves. And if we know where the offset in that DLL contains the function, we can just create a arbitrary pointer to that location in memory and cast it as a pointer to that function. And then later on, we can just do, func pointer and just call it like any other function directly. And that's the approach we're going to do to call getLogObject. So the first step here is to see if you can successfully call getLogObject, which means your harness can load the DLL, it can create a function pointer to getLogObject, it can call it and get a return value from it. Now, what is the return value from getLogObject? Well, it's just going to return something. But it is going to modify Rux. So you should get something out of it. Now, first thing I want to say about this is in order to call the function or create a function pointer, we have to know the prototype, which means we need to know the parameters it takes. Because if it's expecting a pointer in the first parameter and a string in the second parameter and an integer in the third parameter and another pointer in the fourth parameter, if we don't call it with the right parameters, the target may crash because it thinks that in R9 register it contains a pointer to like the fourth parameter, but we never provided that. So it's just going to arbitrarily dereference whatever is contained in R9, right? There could be bugs there. Well, I guarantee you'll come across some wacky behavior if you're not calling it with the right prototype. So that's the first thing we need to do. We need to reverse engineer the parameters that this function takes so that we can call it properly. Now, at this point in time, you may want to pause the video, take a look at this getLogObject, have a go at reverse engineering the parameters yourself, see if you can figure out how many parameters it takes and what types they are. I recommend doing that for a few minutes before resuming. Otherwise, I will resume very shortly and we'll take a look at getting the prototype out and then how we can create a function pointer. And then we'll move on to the next steps. Okay. At this point, you may have had a chance to play with it yourself, or you may just be skipping ahead. Either way, let's take a look at how we can determine what parameters this function takes. Now, first of all, there's a big hint here that says it's a this call. Now, a this call is a type of C++ I guess, construction, where the first parameter in RCX is a object, or it's a pointer to the object of the class. And in this case, the class is event service. We know that because it's event service : get log object. So the first value is a pointer to the event service class. Now, say we didn't know that. Say we didn't know what this pointer was a pointer to. How could we find out what it actually was? Well, the key to that is just finding out where it came from. So let's take a look at what actually calls this function. If I view the incoming calls, I can see that there's two functions that call it: build complex query and register log handle. Let me click on register log handle. Okay, here I can see get log object being called with parameter 1. Where did parameter 1 come from? Let me trace it up. Parameter 1 was the first parameter to this register log handle function. So let's see what called register log handle. I can see one reference to it here. Now register log handle was called with this gservice value. So this gservice value is what is essentially the first parameter to get log object. Now gservice, if I double click that, and I have to view that in the listing view, here it is. It's actually a global. So it's a global that's being passed to the function. Now, in this global, there's a few cross-references to it. Now, I want to look at the cross-reference to it that is of operation type write, because I want to see where it gets set. So if I double-click the more here for the cross-references to this global, and I search by type, I'm going to look for a write. I see a read write and a write. I'm going to go to the write. And I'm going to switch to decompiler view. Okay, so somewhere in here, gservice is getting set. I should have went to the exact location. Let me highlight that and go to the decompiler view. Where is that highlighted? Ah, here it is. Should be somewhere around here. Well, first of all, this function is called global initialize. That name alone kind of makes sense that it's writing to that global, because I guess it's initializing it, right? So that makes sense. Let's take a look. Apparently somewhere around here is where the gservice is being set. Let's try and find it. Would probably be, here we go. I was going to say it would probably be easier if I had the listing view side by side with the decompiler, but that's fine. Here's gservice being set. It's being set to whatever this variable is. Where does this variable come from? Well, if we trace it up just a little bit, I can see it first gets set to pval for, well, actually down here, it gets set to local 2f8. Well, actually, local 2f8 gets passed through to this event service function, and then that gets set. So this event service function is a constructor. It takes in a pointer, and it just sets values in it, because it's a constructor. It'll construct the object by just setting stuff in it and returning it out. So I know just from the fact that this constructor is called, and then the return value from it is set into gservice, that gservice is a event service class object. Now, if I wanted to call this constructor to create my own value that I can pass through as the first parameter to get log object, I need to know the size of the pointer I'm providing it. Now, I could just reverse engineer this and find out what the max offset from that pointer that is used, and then make sure I allocate enough room in the buffer for it. But if I just go back and trace this local 2f8 value, which is used as the pointer, I can see that this is constructed here, where it's coming from an operator new, where the size is 0x1a0. So this is just creating a buffer of size 0x1a0, passing that empty buffer to the constructor, and then setting the return value of that to gservice. And we know that gservice round up being the first parameter to getLogObject. So we can construct the first parameter to getLogObject very easily by just allocating a buffer of 1A0, passing that buffer to the event service constructor, and using that return value as the first parameter. Done. We know the first parameter is an event service type, and we know how we can construct that. So that's the first parameter for getLogObject solved. Now let's go back to getLogObject. What's the second parameter? Well, the second parameter is the first parameter to open external EVTX file. Okay, so what is this parameter used in open external EVTX file? Is the first parameter, let's track its usage. Well, in here, it gets dereferenced and set to 0. Here, it gets dereferenced and set to something else, and then it's returned. And actually, at the bottom here, that same value, that param1, which is actually the second parameter, is what's being returned out. So what that tells me is that this second parameter is used for output. It's used for the caller to get some information out of this function. Because not only is it returned, but if I look at its usage in another function, in open external ETL file, I'll see that this parameter is also just dereferenced and set. It's always only written to, it's never read to. Here it's used in the operator equals to, so it's again being set to this. And if I look at what it's being set to, well, in open external ETL file, it's either set to 0 or it's set to this PL-var2. And this PL-var2 is a external ETL file object. And I know that because it's set to the return value of this external ETL value constructor. Because this is the constructor, right? External ETL file, colon, external ETL file. If I double click that, I see it just creates an ETL file, sets the VF table and returns it. So if we went down this path, it would be a output that contains the ETL file. If I go to the open external EVTX file path, it either gets set to 0 or it gets set to local 60. Local 60 gets allocated a fresh buffer, and then it gets set to a VF table and a VF table for the external EVTX file. So this is actually the constructor here for a external EVTX file. It's just kind of inlined because it's pretty small. It's just allocated to a buffer of 0x18, and then it's set to the first VF table entries for the external EVTX file class, and then that's set to the param1 output. So if I go to getLogObject, I know that the first parameter is a event service object, which I'm just going to leave as named this. We know that the second parameter is an output value, and it's going to be one of the EVT, EVTX, or ETL file outputs. So I'm going to name this plogout. It's P because it's going to be a pointer, so it needs to hold enough space to contain a pointer. And it's going to contain a log file, either EVT, EVTX, or ETL. And I marked it as out because it's an output that's going to come back to us. We're going to use this second parameter to get information out of this function. It's not an input. It just needs to hold a 64-bit value. Well, at least on a 64-bit operating system, because the target is setting it to a pointer to a EVTX file or an ETL file. And a pointer on x64 is 64 bits. Okay, so at this point, it's like, okay, I find out what the two parameters are. Is that it? Well, actually, no. In this case, Ghidra is lying to me. There's more than two parameters. There's actually a third parameter. Now you might think, how do you know that? Well, a couple of reasons. First one is, if I look at the decompiler view, I see this in R8. And in R8, it's like, where did that come from? Right? It's not actually a stack thing. If I look at the listing, um, it puts R8 into, yeah, it just passes R8, which is, if you know what the calling convention is on x64, the first parameter is RCX, second one's RDX, third one's R8, fourth one's R9, and then the rest will be on the stack. Um, in this case, it's passing R8 to determine file type, and then the determine file type is actually doing stuff with that value. So it does actually expect a value. And if I look at the disassembly listing for this, you can see that R8 is being moved to this. Now this actually threw me off, but the this is actually RCX because it's using the symbol information that it knows that the first parameter is a this pointer. This is actually going to be RCX. So it's putting R8 into RCX and it's calling determine file type. So the first value in determine file type is going to come, it's going to come from R8. And R8 wasn't created in this function. There's nothing setting it. So it has to be something that existed before this function was called, which means it's a parameter. So how can I do that? Well, first let's find out what value it is. In this case, it thinks it's a pointer. And actually, if I go to determine file type where it's used, we can see that that parameter is passed to file exists, is passed to create file W, and create file W does take an ALPCW string. So that's going to be what this parameter one is. It's going to be a wide character string pointer. And it's going to be the pointer of a file. And we actually saw that this is where our file gets read by 8 bytes. So this is going to be our file name to our EVTX file on disk. So I'm going to edit the function prototype for getLogObject by doing right-click, edit function signature. I'm going to hit the plus and say that there's a third parameter. It is a wcar underscore t pointer. And I'm going to name it EVT file path. And hit OK. Now I can see that that is properly passed to determine file type and open external EVT file and EVTX file, etc. And now everything makes sense. There's no variables that are being used that come from nothing. The first parameter is this parameter that's being passed fine. The output value is being passed fine. The third parameter is being used fine. There's nothing else that looks suspicious in this output. So at this point, I'm happy with this prototype. Now you could verify this by attaching a debugger to the process that calls getLogObject, and then hitting a breakpoint on this function and dumping out what the third parameter is, what the second one is, what the first one is, and analyzing it dynamically. But in this case, we didn't have to. Now that I know the function getLogObject, and I know the parameters it takes, and I know how to create them, right? The third parameter is just a wide character string to the EVTX file on disk. The second parameter just has to be a pointer to a buffer large enough to hold another pointer. And the first parameter is a event service object that we know we can create because it's that 0x1A8 or something size. And then you just pass that to the constructor. And you can call the constructor by creating a function pointer to it. So now at this point, we know what we need to do. We need to, 1, load revt service.dll into our process. 2, create function pointers to event service constructor. And to getLogObject. 3, construct the parameters for getLogObject. 4, call getLogObject. Right, we've identified these steps. Load the DLL, create the function pointers, construct the parameters for getLogObject, and call getLogObject. And then make sure we get a result from it and that there's no crashes. make sure it works with no crashes. Right? We're expecting this process of calling getLogObject to not crash. Now that we know what to do, this is the next challenge. I've provided a starting file, a starting C file or C++ file that will show in code how to create a function pointer and how to define what arguments that function takes. So now your next steps in the challenge is to perform these steps of being able to successfully call getLogObject without crashing. And you can verify it by verify return value for arg2 contains a valid pointer. So it's returning a value that's also going to be set to your argument 2, and that's going to contain a pointer to something. So if you first provide argument 2 as a pointer to a empty buffer, you should get a different pointer back if the call was successful. You can just also check the return code and make sure that the return value is not 0. Once you've had an attempt at this, feel free to look at the solution before we move on with the next steps.